Hello Math 8 students, this is Utah Middle School Math Project 2.2c, Representations of a Linear Context. To get started, we have a story. Courtney is collecting coins and she has 2 coins in her collection to start with. She plans to add 4 coins each week. So let's take that information, let's organize it in a table. What is going to go here? 0 weeks have passed. So how many coins does Courtney have? Aaliyah, are you sure? Read the situation one more time. How many coins does she have? 2. Yeah, she has 2 coins to start with. But now 1 week has passed. And what happens in a week? She adds 4 coins. So how many coins does she have at the end of the first week? Weston? Who can help him out? Ozzy? 6, because if she has 2, and she's adding 4 each week, 2 plus the 4 that she just collected means that she has a total of 6. Well, another week passes. How many coins is she collecting each week again? 4. So how many coins does she have now, Caleb? 10. You get the idea. How many coins now after 3 weeks? Weston? 14, because 10 plus 4 is 14. And 4 weeks have passed. So how many coins now, Cadence? 18. And then 4 more coins means now we're at 22, and 4 more coins means now we're at 26, right? Question for you. There is no 7 on the table. I'm not going to put it there, but I am going to skip ahead to an 8. How many coins is she going to have after 8 weeks? Talk at your tables and see if you can figure that out real quick. Am I still going to be adding 4 here? Okay, come back and tell me, how many coins do you think she's going to have after 8 weeks? Let's go, Michael. 34. How'd you get that? Yeah, it's 2 more weeks, exactly. So here, every week we're adding 4, right? We're adding 4 because 1 week has passed. And another week passed, so we add 4 coins. But here, how many weeks passed? 2 weeks passed, so it doesn't make sense that we would only add 4. 2 weeks passed, so how many coins is she adding to her collection? 8, exactly. All right, next challenge, we need to create a graph, choosing an appropriate scale. So a couple of things to note. Remember, first column is our X column. Second column is our Y column. So this is our X-axis. This is our Y-axis. That means, what label am I going to give to the X-axis? I'm not just going to call it X. I'm going to call it, what am I measuring? Time in weeks. And the Y-axis, I'm not just going to call it Y. What am I measuring? What's the label? Coins. Okay, labels are done. Now it's time for the scale. What are we going to count by on the X-axis? Look at our data. How often are we measuring this? Weston? Yeah, going by ones. So here's an X value of 1 week, 2 weeks, and so on. I get to be lazy, so even though I know that this is a 4, I'm not going to write it down. I'm going to move on and write a 5 on the next one. So it's okay to be lazy. Just make sure that you know that every single time we are counting by ones. Check in with your tables. What are we going to count by on the Y-axis? What is an appropriate scale? Check in with your tables. Ready, set, go. All right, what are your thoughts? Kale. We can count by 4s. What do you guys think about that? It's all right. Why is it only all right and not great? We're counting by 4s here, aren't we? Weston.
It's all right to count by 4s, but to get it right, you can go across the table multiplying 2.
We could count by 2s. So when I say we're counting by 4s, are we really counting by 4s? Are any of these multiples of 4? No. We're going up, we're increasing by 4, but none of these are multiples of 4. So let's start looking at, if I count by 4s, what's that going to do? Over 0 and up 2. Is that going to be a crosshair point? No. Over 1 and up 6. That's going to be partway between the 4 and the 8. Is that a crosshair point? No. So can we make it work? Yeah, we can. Is it going to be perfect and great and ideal? No. What is the number that we could count by that will make them all land on crosshair points? Yes, Seth. We could count by threes, but are they all going to land on crosshair points? How did I hear three? I don't know. Twos? I like twos way better than threes. Let's look at twos. Are we going to have some nice crosshair points if I count by twos? Yeah, 2, 4, 6, 8, 10. Let's just stop and see for a second. Over 0 and up 2. Yep, that's a nice crosshair point. Over 1 and up 6. Yep, that's another nice crosshair point. So counting by 2 seems like it's going to work pretty nicely. Now, if you decided to count by 4s, is that fine? Yep, it'll be fine. It just might not have it quite as neat, but it will definitely be fine. 14, 16, 18, 20, 22, 24, 26, and 30. All right, we've confident. Okay, Philip, what's the slope of the line? We can come back to you, Philip. What is it, Kale? Slope is 2. Who agrees? Good. I disagree. Sure, I might be going up 2 and over 1. So why is the slope not 2 when clearly I'm going up 2 and over 1? Talk at your table, see if you can figure out the mistake. Because a lot of you guys think it's 2. It's wrong. So what's going on here? Okay, what is the slope of this line? Philip. Nope, it's not 2 plus 4. What is the slope? Remember, slope, folks, this is how I know you guys were not paying attention the last time. It's all coming clear. Slope is the rise over the run. What's the rise? Is it though? Is it though? I'm going from 10 to 14. How much am I rising? 4. You have to pay attention to the scale. Remember the scale that you guys chose? Remember that? Remember how you even chose it? We have to watch that. We're not just counting grids. We're not just counting boxes. How much am I going up? If I'm at 10 and I'm going up to 14, how much am I rising? 4. How much am I running? How much am I going over? 1. Why is this a 1 and this a 4? Because I'm going from 2 to 3. So how much is that changing? 1. We should probably write this down because you guys struggled with that way more than you should have. What is the slope? The slope is the rise over the run. But what is the rise? We're going up 4. What is the run? We're going to the right one. And what is 4 divided by 1? What does that simplify to be? That is 4. Everyone with me? Okay, we have a challenge. It says we need to write an equation for the weeks and the coins. It says we want to use C and W, and that's fine. We will use C and W eventually. But since we already have an X and a Y, can we write an equation for an X and a Y? Again, to reiterate, we're writing an equation X and Y. We'll change it to C and W later. But how are the X and the Y related? How are the weeks and the coins related? Pausing the recording as students discuss. Okay. Who would like to give it a try? Ozzy. It is adding not each day, but each week. Yep, we are adding 4. But what is that going to do for the equation? Michael? Yeah. Y equals 1x plus 4. Or just x plus 4, right? Okay, y is equal to x plus 4. Let's test that out and see. Let's pick a y value. I don't know, like maybe this one. This is a good one. So here's a y value of 22. How did we get there? Because we took the x value, which is 5. Ooh, that doesn't seem to work, does it? So this is important. You're recognizing an important relationship, but you're misusing that important relationship. You're recognizing that going down the table, I'm adding 4. Guess what? I don't care about going down the table. I need to go across the table. How am I going across the table? That's how we write an equation. The plus 4 is important. You're misusing that information, but recognizing that there is an important relationship with adding 4 coins each week, that's great. Weston, what do you think?
I'm thinking, so since we're going across the table, isn't it like y equals x times 2?
Okay, y is equal to x times 2. Let's test that out. Let's pick a y value. 22. What's the x value that goes with it? 22 is equal to 5 times 2. That didn't work either, did it? Why did you choose the 2?
Because we're going across the table when, because we're going up, we have to go across the table to get it.
Yeah, we do have to go across the table, but why 2? Where did the 2 come from?
She originally started out with 2 coins.
Okay, so again, you're noticing something really important. How many coins do we have in the beginning? 2. That's just as important as recognizing that we're adding 4 each week. Take both of those pieces of information. Michael knows we're adding 4 coins each week. Weston knows we started with 2 coins. Put that information together and write an equation. One last chance with your tables before we come back together as a class. Pausing the recording as students recheck in. Ready, set, go. Okay. I know for sure that Alexis has this equation because I heard her talk to her group about it, so I'm going to come back to you. I don't know if anyone else does, so we're going to baby step this. I have a question for you. In 1 week, how many coins did she collect? Not does she have total. How many did she collect in 1 week? Michael? 4. Okay, what about 2 weeks? How many did she collect? How many total has she collected? Cadence? Yeah, total collected, not the grand total that she has. 8. Okay, where'd you get that? You're right, but where did you get it? Yeah. The week multiplied by how many coins is she collecting each week? 4. Let's skip ahead. 5 weeks. She's been collecting coins for a long time, right? So how many coins has she collected so far? How many coins has she collected after 5 weeks? 4 here, 4 here, 4 here, 4 here. How many in 5 weeks has she collected? How many, Alexis? No. Listen. Voice is off. You're not listening. Guys, I'm not asking how many total coins. Just how many has she collected. So week 1, she's collected 4. That's why she has a total of 6, because she started with 2. Week 2, how many has she collected? 8 plus the 2 that she started with. We're skipping ahead. Week 5, how many has she collected? 20 plus the extra 2 that she started with. Do you realize what you're doing? Every single week, whatever that is, she has collected 4 coins. But is that all of the coins that she has? No, because she also started with 2 extra. Alexis, what's your equation? Yep. X times 4 plus 2 is equal to y, the total. Y, where is that coming from? Why are we multiplying this by 4? Put it in your own words and talk with your tables. Why are we multiplying this by 4? Okay. Why are we multiplying it by 4? Weston.
It's because
Yeah, because she's collecting 4 every single week. So it's the weeks multiplied by how many coins she's collecting each week. But then why are we adding 2? What does that mean? Why are we adding 2, Mappa? We started with 2. We can't forget about those 2 that we started with. She's not collecting those 2 every single week, but she still started with them in the beginning. That's why she decided to start collecting coins. So let's manipulate this equation. Because in 8th grade, we typically don't write it like this. We're going to write y is equal to, instead of x times 4, we're going to say 4x, right? We know this. And plus 2. And now we're also going to continue to manipulate this. It doesn't want us to use x and y. It wants us to use c and w. So let's make one more manipulation. The w represents the weeks. The c represents the cost. Or sorry, the coins. You're right, the coins. So instead of x, I'm going to write w. So w times 4 plus 2 is equal to, instead of y, I'm going to write c. But since we're in 8th grade, we're going to write c is equal to 4w plus 2. There's 4 different versions of this equation, 4 different versions of this relationship. Okay, are you with me now? Question C asks, is this context linear? Let's talk about the meaning of that word. We've heard it before. What does linear mean? Kale? Yeah, exactly. So we're asking, is this a straight line relationship? Well, let's start with the easy one. Let's look at the graph. Is this a straight line? Is it a line? Yeah. Does it do anything weird, like curve like this? No, it doesn't go through the origin. That would be proportional, but is it a straight line? Okay, so when I look at the graph, can I tell that it's a straight line? Absolutely. How can I tell that it's a straight line? We're going to offer evidence for each one of these. So I'm going to start with graph. Is it linear? Yeah, it's a straight line. But I want us to focus on what makes it a straight line. When I look at that relationship, what made it a straight line and why? Remember how I reached that certain point where I'm like, I'm done drawing all of these points. I'm just going to make it a straight line. Remember that part? How did I decide that I could do that? What is it about the way those points were lining up and showing up on the graph that made me decide that? Talk at your tables really quick. All right, what is it about this relationship that I decided I could just make it a straight line? What did you notice? Weston?
So I noticed that it has a constant of proportionality.
Ooh, does it have a constant proportionality though? If it's not a proportional relationship. It Okay, that's better. That's better. It's not that it has a COP. There's no constant proportionality, but we have this constant pattern of going up 4 every time I go over 1, right? Everywhere I look on this graph, I can go up 4 and over 1. What is that called? What is that called? Seth? Slope, yeah. So it's a straight line. Why is it a straight line? Because it has a constant slope. I'm always going up 4 and to the right 1, up 4, right 1, up 4, right 1. That's what makes it a straight line. Now, with that in mind, are you ready for the challenge? We never graphed it. That never happened. You can't see that. Okay? All you have now, oops, I don't want to. All that you have now, folks, is just the table. Graph is no longer there. Can you still tell if it's linear? Can you still tell if it's going to make a straight line? Look at the table. What information do I see that's going to tell us that? Talk at your tables. See if we can figure it out and come to a conclusion. Okay, let's come back together. Who would like to share for the recording and share for the class? Aaliyah, what are your thoughts? Okay, they're all even numbers. You're on the right track, but it's even more important than that. Because even if they were all odd numbers, I could still see the same relationship. So it's more than just that, but you are looking at the right things. Micaiah, Sorry, say that again. They do though, because it was 6 and then it changes to a 10 and then it changes to a 14. Ah, that's the numbers that don't change. In how they change, it doesn't change. How does a 2 change to a 6? It's because we're... try again, try again. Watch your words. How is a 2 changing to a 6? Adding 4. Not multiplying by anything. Why am I adding 4? Because 1 week passed. Why did I add 4 here? Because 1 week passed. Why did I add 8 here instead of 4? We had this nice pattern where it was never changing until it did. Why am I adding 8 here? Talk at your tables. There's not enough hands. Why am I adding 8 here? Okay, Michael. Yeah, 2 weeks passed. So even when it does it change in a way that's predictable and that we understand? Yeah, why did the 26 jump 8 instead of just 4? Because the 6 also jumped to an 8 instead of to a 7. Do you know what you just found? You found the slope. Because this is how the y values are changing, and the y values go up and down. Therefore, this is our rise. The x values go this way. We found out how the x values are changing, so we found the run. You found the slope. Even without needing a graph, you found the slope. Let's write that down. What did I see in the table to help me know that it was linear, that it had a constant slope? The y values changed. I can say this a lot simpler. Instead of saying changed, I'm going to say increased by 4. I'm sorry. Y values increased by 4. Every time the x values increased by 1. Again, that's the slope. But normally we think about slope when it's on a graph. So when it's not on a graph, if it's in a table, yes, it's still slope, but we can more easily think of it as the rate of change. Rate meaning ratio. We're comparing the ratio of how the y values changed to how the x values changed. That still is the same as the slope. Okay, it's getting harder now. Guess what? Eventually this is going to happen. You no longer have a table. You no longer have a graph. I don't want to lock in place. I'm trying to bring it to the front. Okay, all that information is gone. All you have is this. You have a table. You have an equation. Or sorry, you don't have a table. You don't have a graph, but you have an equation. Can you still tell that it's linear? Yeah, 4 is that magic number, isn't it? Do you still see that 4? Yeah. So one thing that you might remember from our last lesson, equations of linear relationships are always going to be in the format y is equal to some number multiplied by x, which we have. And it's okay if they also have an extra number added on at the end, a different starting place than the origin. So, is this equation in that same format? Maybe we're using c instead of y, but I have c is equal to some number times another variable plus wherever I started. So is it in that correct format for a linear equation? Sure is. And last one, it says context. Context is just a fancy word for story. Is there any information in how the story was told that clued us in that it was going to be linear? What do you see? Adding 4 coins each week. Even in how they told the story, they told the story that there was a constant rate of change. Constant rate of change. We're constantly adding 4 coins each week. Okay, let's move on to the next story. I know some of you are still writing, so I'll give you just another second. Those of you who are ready, start reading ahead to the next story. Start filling in that table. Looks like everybody's done writing down, so I'm going to move on. In this next story, Jack is filling his empty swimming pool with water. The pool is being filled at a constant rate of 4 gallons per minute. Let's fill in that table. How much is starting in the pool? Does it tell us? Yes, it does. Read it again. Yeah, empty. What does empty mean? 0. So how much water is in the pool right now? 0, but 1 whole minute has passed, and he is filling the pool at a constant rate of 4 gallons per minute. So wait a second, 1 minute of time has passed. So how many gallons were just added to that pool? 4. How much is in the pool now? 4. All right, 1 more minute has passed. That means I know I added 4 more gallons to the pool. So what's in the pool now? 8. Keep going. This is not a big pool. We don't know yet. We're only making it to 6 minutes, but this is not a big pool. This is like not even the size of a bathtub yet. Does your table look like mine? Okay, let's do something fun and more interesting. Let's skip ahead to 10 minutes. Because pools take a long time to fill up, right? So let's just come back in 10 minutes. How much is going to be in that pool? Start talking with your table. How are we going to figure that out? All right. I know that there's 40. How did I get there? There's lots of ways. Who can tell me one way? Tell me one way, Mappa. Yeah. 4 times 10. Whatever the minutes are, we're just going to multiply it by 4. And that's how many gallons there are, right? Who found it a different way? Kale. Good. That is a relationship that only works because this is secretly, fun fact, it's proportional. Only because it goes through the origin that we can do that. But that is, because let's look at the other one. Did that work over here? Let me delete this now. 2 doubled is 4, but 10 doubled is not the 18. So it doesn't work there. It only works this time because it's proportional. Take a look at this one though. This relationship will work no matter what kind of thing we see. Let me show this one. We're adding 4 every single time, right? Until we're not. Why am I not adding 4 here though? How much did this change? Yeah, how many minutes passed? Not just 1, but... So how many gallons would I have added in that amount of time? 16. Yep. Lots of ways that we can do this. Here's the easiest way. How am I going across the table? 10 multiplied by 4 is 40. We'll get there. That's an equation, part B. Let's hurry and finish graphing this though. Pretty easy after our last one. Here's our x, here's our y. So this is our x-axis. We're measuring time in minutes this time. Not in weeks, but in minutes. Water is measured in gallons. I still think that the appropriate scale, we're measuring each minute. What is an appropriate scale for gallons? Quick check-in at your table. Gallons, what's going to be a good scale to count by there? You want to do 2s like last time? Yeah, is 4s going to work this time? Better than the last time, right? So can I count by 4s now? Yeah, I can. You make a choice. Do you want to count by 2s? Do you want to count by 4s? That's up to you. Four, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, and 60. Yeah? Let's graph. Where am I starting this time? With an empty pool. It goes through the origin. That makes this one proportional, where the other one was not. Over 1 week and up 4. Over 2 weeks and up 8. Over 3 weeks and up. Hey, wait a second. Do you notice something here? Could I just maybe be lazy and make this a nice straight line? Yeah, we're seeing this constant pattern. Let's take advantage of that. What is this? Yes, Micaiah. Did I say weeks again? I'm sorry. Good job. Good catch. What is the slope of this line? Check in with your tables. What's the slope of this line? Is it 4 or is it 1? I'm hearing some of both. It's 4. Don't fall for the same tricks that you guys fell for last time. Sure, I might be going up just 1 box, but that is going from 12 to 16. So how much am I really going up? 4. How much am I going over? 1. So the slope is 4 or 4 over 1. Let's write that equation. Let's start simple with x and y. How is that x changing to a y? How's a 4 changing to a 16 or a 5 to a 20? Or how did the 10 change to a 40? Y equals 4x. All I'm doing is simply multiplying by 4 as we go across the table. So x times 4 is equal to y. Y equals 4x. Only now let's use the variables that it tells us to. It wants us to use m for minutes and g for gallons. What's that equation going to be then? M. Finish it up, Weston. Ooh, so close. Let's test it out. Let's pick anywhere on the table. Let's pick this spot right here. M, the minutes, is 5, is equal to 4 times the gallons, which is 20. Is that true? Is 4 times 20 equal to 5? No. What fix do you need to make, Weston? Is M equal to 4G? What is? Mappa? Yeah, G is equal to 4M. Let's test that out. Pick a spot on the table. 5 is the minutes. 5 times 4. Is that equal to the gallons? Yeah, that one works. Always good idea to test your equation, especially when we're using variables that are maybe not x and y. G is equal to 4 times M. You can also say y is equal to 4 times x. Key thing, what are we noticing in this equation? There's that 4 again. So, once again, is this context linear? Let's look at the graph. Is it a straight line? Yeah. But it's more than it just being a straight line. It's a straight line because it has a constant slope. Okay, I'm taking away that graph. You can no longer look at the graph. All you have is a table. Can you still look at the table and tell if it's linear? Yeah, what are we seeing? Up 4 every time this goes, up 1. Up 16 when it went up 4, which still simplifies to the same thing. So the table also has a constant rate of change. What I'm really saying is the y's continuously go up by 4 every time the x's continuously go up by 1. What about the equation? Remember how I said that the equations are always going to be in that format, y is equal to something times x plus something else? Is it in that same format? Do we have something times x? Yep. Do I have plus something else? Or do I? If the pool's empty, what does that mean? Plus 0. We're lazy though, so we don't normally write it down, but does it still fit that format? Yeah, it just happens to go through the origin because it is empty. It's proportional. And the last one, what in the story tells us that it's going to be linear? Go back and read the story again. There was a clue. What is the clue in that story? Ariel. Exactly. It tells us that it's a constant rate. So we know right in the beginning that it is a constant rate. It is going to be linear. All right, now is my favorite part of this lesson. How is this problem and our coin problem that we did previously, how are they similar and how are they different? Micaiah already caught me on saying the names wrong because they are so similar, I was getting them confused. Will you talk with your tables? How are they similar and how are they different? Check in, ready, set, go. Okay, tell me what you know. Let's start with Micaiah. Perfect. Starting places were different, right? One started at 0, one started at 2. What is the same about each of them? Alexis. Exactly. Both adding 4 each one, right? Fantastic. So let's change them. If I wanted to change the coin story, so remember Courtney collecting coins, if I wanted to change the coin story so that I could represent it using this table and this graph, what change would I need to make to that story? Give you a couple of extra seconds of thinking time here. What changed would I need to make to the coin story? Weston. Exactly. Courtney would have to start at 0 coins. Okay, similar question. What if I'm going to change the swimming story? So I'm going to change the swimming story because I want it to match this table and this graph. What change do I need to make to that story? Michael. Yeah, he starts with 2 gallons in his pool. It's not empty yet. There's 2 gallons in it. Jack's pool is not empty. Jack has 2 gallons in his pool. All right, let's move on to the next one. Okay, what do you notice? This one is interesting because this one, we can see that we have a starting of 3,000. So this one's definitely not going to be proportional. Something else that's very interesting is when we look at the change, we can see it goes from 3,000 to 2,000. So it's the first time we've seen this one. That means this one is actually decreasing by 1,000. And we continue to look further at this table, we can see, yes, it is continually decreasing 1,000. But how often is it decreasing 1,000? Look at how the miles are changing. The miles are changing from 0 to 2. And then again from 2 to 4. So I want you to think about this in terms of the slope. What is the slope going to be given this information? As we've seen throughout this, this is going to be our x, this is going to be our y. So if I'm looking at this is the y values and how the y values are changing, that's the rise. This is the x value and how the x values are changing, that makes that the run. So if I want the rise over the run to figure out the slope, I can see that is going to be negative 1,000 with a run of 2. And that just simplifies to negative 500. Let's create a graph. So again, we've got our x-axis. We've got our y-axis, and I was so excited about this problem I didn't even read the story or the situation. It says an airplane is at an elevation of 3,000 feet, and the table shows the elevation, which is the y, for every 2 miles, which is the x. So again, the x is representing the miles. And the y is representing the elevation. That would be the elevation measured in feet, I imagine. So what are the appropriate scales here? Miles. You might be tempted to say, let's count every 2 because this goes 0, 2, 4, and that's fine, but we've got so much space it also makes sense to count by ones, focusing on the second one, the fourth one, and the sixth one, just like it does in the table, but we could still count by ones here. The elevation, it starts at 3,000. That means I definitely should see the 3,000, so what kind of scale do I need in order to make sure that I start at 3,000? If I count by 500s, that'll do it. So 500, 1,000. It makes that 2,000, and this 3,000. And now I'm ready to plot those points over 0 and up 3,000, just finding that information here in the table. Over 2 and up 2,000. Over 4 and up 1,000. And I'm starting to recognize that this is making this nice pattern, beautiful linear relationship. Use the table and the graph to find the rate of change. I've already done that. I found that rise and that run. The rate of change, the change in the y values, and the change in the x values. But can I see that same information in the table or in the graph? Let's measure that slope. How much am I going down? I'm going to choose these crosshair points that are already on here for me. Going from 2,000 down to 1,000, that's negative 1,000, negative because I went down. And the 2 is changing to a 4, so that means I'm going over by 2. And again, that rise of negative 1,000 and the run of 2 will simplify to negative 500 every 1 mile, or simply negative 500. Write an equation that represents this relationship. Again, this is different than the other ones, but based on what we have already seen, we know how important that rate of change is in our equations. We also know how important where we're starting is in the equations. So take a second and pause the video and see if you can write your own equation. And again, what I'm seeing in this relationship, we are decreasing by 500. So that is our rate of change, but I had a starting value of 3,000. So negative 500x plus 3,000 takes into account both the rate of change and the starting value or the y-intercept. Explain how that equation can be used to determine how many miles it will take for the plane to reach the ground. Well, I've already seen what that looks like in the graph. Here's the elevation of 1,000, 500. That would be an elevation of 0, or also known as that ground. So how long does it take for the plane to reach that? That takes 6 miles. How can we use the equation though? We're using it in the same way. So again, if I've got this equation as y is equal to negative 500x plus 3,000, what I'm telling you is the y value is 0, because the y value is 0 means I've reached the ground, an elevation of 0. So that means I'm just going to substitute the y for a 0, plug it in, and solve to figure out what the x value is. I'm going to undo adding 300 by adding 3,000 by subtracting 3,000, keeping it balanced and doing the same thing to the other side. 0 minus 3,000 is a negative 3,000, and that is equal to negative 500x. X is multiplied by a negative 500, so I will undo that by dividing by a negative 500, again balancing it, doing the same thing to the other side. And that means I have x is equal to, type it into your calculator if you need to, negative 3,000 divided by negative 500 is equal to a positive 6. So how many miles for the plane to reach the ground? That would be 6 miles. That's it for today's lesson. Your homework is 2.2c homework section. All problems, there's only 3 of them there. Make sure you get that done. We'll see you next time.